This is Algebra Lesson 6-4, Applications of Linear Systems. Now, before you can solve any type of word problem, you have to determine several things. There are some very good questions to ask yourself after you have read over a word problem. Sometimes after you've read over a word problem several times. Number 1, what do I know? Number 2, what am I trying to find? And number 3, what can I find using the facts that I have? Now, we have 3 methods for solving systems of linear equations: graphing, substitution, and elimination. Graphing is good for solving systems that are easily graphed or are very visual, or perhaps when you want to estimate a solution. Substitution is very helpful when one equation is already solved for one of the variables, or when it is easy to solve for one of the variables. And elimination is easy to use when the coefficients of one variable are the same or opposites, or when it's not convenient to use graphing or substitution. So let's take a look at a couple of things that we're going to be doing. One of the things that we're going to work with is we're going to work with what's called a break-even point. A break-even point for any type of thing like a business, or for maybe you are trying to break even on a fundraiser of some sort. Break-even point is the point at which your income will equal your expenses. So let's say you're doing a car wash. Your break-even point is when the amount of money you spent on the supplies for your car wash, like soap and buckets and scrub sponges and window cleaner and all of that stuff, whenever that equals however much money you bring in, that's called your break-even point. Okay. The graph to the right here shows the break-even point for one business. Notice you'll see 2 lines. You see the greenish blue type of line, which is the income, and the red line, which is the expenses. Okay. The point where those 2 lines intersect is what we call the break-even point. Before that break-even point, where you see the light white color of the graph, you're losing money. You're spending more money than you are bringing in. Where you see the yellow highlighted portion of the graph, that's where you're making money, which means you are bringing in more money than you spent in your expenses. Okay. So you use y to represent both expense equations and income equations. So let's take a look at a problem. We're going to find a break-even point. A carpenter makes and sells rocking chairs. The material for each chair costs $22.50, and the chairs sell for $75 a piece. If the carpenter spends $420 on advertising, how many chairs must she sell to break even? So, sometimes you need to read the question several times. The first thing we need to do is, what do I know? Well, I'm looking at this saying, I know how much it costs to buy the material for each chair. I know how much they sell each chair for, and I know how much they spent on advertising. What am I looking for? How many chairs must the carpenter sell to break even? So I'm going to have 2 variables here. All right, I'm going to have an x variable and a y variable. And my x variable is going to be the number of chairs I need to sell. Number of chairs sold. And y is going to be my total. And we'll call that dollar amount. So I have 2 equations I need to make. Sometimes they call y the total incomes or expenses, but it's just easier if I just realize I need to make 2 equations. I need to make an equation on expenses. What does it cost the carpenter? So my expense equation, the total for my expense equation, is going to be the amount of money that I spent for the materials to build each chair, plus the amount of money I had to spend on advertising. All right, so this would be 22.50x, because it's $22.50 per chair, plus $420 in advertising. And then my income, how much money is the carpenter bringing in? Well, they're bringing in $75 a chair. So that would be y equals 75x. Now, this is a perfect example of an equation which would be easily solved by substitution. Since both equations are in y equals form, I just need to substitute in one y in one equation into the other y of the second equation. Okay, so I will just number this first, the top equation 1 and my bottom equation 2. So I'm going to take equation 2, and every time I see a y, I'm going to substitute in 75x. So in equation 1, every time I see a y, I'm going to put in 75x. So this 75x is going to move into that portion of the equation. So I have 75x equals 22.50x plus 420. Now I have this all in terms of one variable, fairly simple to solve. I'll subtract 2250x from both sides. 75 minus 2250 is 5250. And that's going to equal 420. To solve for this, I'm simply just going to divide by 5250. So x is going to equal, when I divide 420 by 5250, I get 8. So how many shares must you sell to break even? Well, that was the number of shares needing to be sold would be 8, so I've solved my equation. So she needs to sell 8 shares. So that's an example of a break-even equation, a problem, where we solved it by using a system of equations. Let's take a look at another problem. Number 2 here. A metal worker has some ingots of metal alloy that are 25% copper and others that are 50% copper. Okay, an alloy just means it's a mixture of metals. How many kilograms of each type of ingot should the metal worker combine to create 40 kilograms that are 45% copper alloy? All right, so let's take a look at what I have. Okay, what do I know and what do I need? They have metal alloy that's 25% copper and others that is 50% copper. And we're looking to make a mixture that is 45% copper. We have a total of 40 kilograms. And we're asked to find how many kilograms of each type do we need to sell or to combine. So in this particular case, since I'm looking for kilograms of each type, I'm going to let x equal kilograms of 25%, and I'm going to let y equal kilograms of 50%. Okay, so I need to know how many do I need to mix together to get it to be 45%. Okay, we know that they want to create 40 kilograms. So one of my equations has to be based upon the number of kilograms that I'm going to have total. Okay, so the first equation is going to be based upon the mass of the alloy. Okay, so the number of kilograms at 25% plus the number of kilograms at 50% cannot exceed 40 kilograms. It has to equal 40 kilograms. Okay, the other one is going to be the mass of the copper. Now the mass of the alloy is going to be slightly different because these have a specific, let's just do it this way. Let's make a mass of copper because I'm going to confuse people if I don't. If we don't make sure we take in the percentage in consideration here, we're not going to have a very good example of this problem. Okay, so I need, okay, how many kilograms of each type of ingot must be the metal worker to create 40 kilograms of the 45%. So I need a certain amount at the 25% and I need a certain amount at the 50%. I don't know how much at either one, but I know however many kilograms I use at the 25%, I have to multiply that by 0.25 because 25% as a decimal is 0.25 plus 0.50y is going to give me, I need 40 kilograms at 45%. So I need 40 kilograms at, 45% times 40 kilograms. So 0.45 times 40. That's my second equation. One is based on the mass of the alloy, and one is based on the mass of the copper. Okay, so let's simplify equation 2 because I need to multiply what 0.45 times 40 is. So I'm going to have 0.25x plus 0.50y is going to equal 18, because 45% of 40 is 18, which makes sense because 50% of 40 would be 20. Okay, so I have my two equations. I'm going to actually solve this equation using substitution because I think it's going to be easier than trying to multiply by decimals and getting some interesting answers there. So I'm going to take my first equation here and I'm going to solve it for x. So x is going to equal 40 minus y. So in equation 2, every time I see an x, I'm going to put in 40 minus y. So I have 0.25 times x, which is 40 minus y, plus 0.50y is going to equal 18. So let's distribute. 0.25 times 40 is 10, minus 0.25y plus 0.50y equals 18. 10 stays. Negative 0.25 plus 0.50. It's kind of like saying 25 cents, negative 25 cents plus 50 cents. So that ends up to be 25 cents. That's going to equal 18. So subtract 10. Subtract 10. I'm going to have 0.25y. It's going to equal 8. Divide by 0.25. So y is going to equal 32. So if y equals 32, and we know that x equals 40 minus y, which is 40 minus 32, x is going to equal 8. So we need, the metal worker needs 8 kilograms at 25% and 32 kilograms at 50%. There we go. And that kind of makes sense because 45% is much closer to 50 than it is 25, so you'd need a lot more of the 50% to bring that alloy percentage up. Okay. Now, in real-world situations, you need to consider the constraints described in the problem in order to write equations. Constraints means restrictions. Okay? Kind of like when you ask your parents if you can go to the movies on Saturday, they might say, you can only go to the movies if you have your homework done and you've cleaned your room. Those are the restrictions that they put on you. Those are the constraints. Okay? Once you solve an equation, you need to consider the viability of the solutions. For example, a solution that has a negative number of hours is not a viable solution. We've talked about this. You can't spend a negative amount of money. You can't have a negative amount of an item. I can't say, I'm going to go buy negative 25 flowers. No, you're not. That's like going to the flower store and handing them flowers and paying them to do so. All right, so let's take a look at this next problem. It says, identify the constraints and viable solutions. Dylan is filling a 20-gallon tank and a 30-gallon tank for his fish display. The 20-gallon tank contains 4 gallons of water and is filled at a constant rate of 10 gallons per hour. The 30-gallon tank already contains 13 gallons of water and is filled at a constant rate of 7 gallons per hour. When will the two tanks have the exact same amount of water? Okay, so it's asking when, that means time, and how much water. So that's going to be an amount. So I'm going to let x equal my number of hours. And I'm going to let y equal the total amount of water. Okay, so I'm going to have two equations because he has two tanks. He has a 20-gallon tank and a 30-gallon tank. Okay, so my first equation says that he's filling a 20-gallon tank and a 30-gallon tank. The 20-gallon tank contains 4 gallons of water, which means it already has 4 gallons of water in it when he starts to fill it with water. Okay, and it's going to fill at a rate of 10 gallons per hour. So the total amount of water in the 20-gallon tank is going to equal the 10 gallons of water per hour, so 10 times x, plus the initial of 4 gallons it started with. So 10x plus 4. Equation number 2 here, we're going to start talking about the 30-gallon tank. Now the 30-gallon tank contains 13 gallons of water and is filled at a constant rate of 7 gallons per hour. So the total water in the 30-gallon tank is going to be 7 gallons per hour, so 7 times x, plus the initial amount it started with, which was 13. Okay, now this is another problem in which I'm looking at this going, wow, substitution would be simple with this, because I have both of these in terms of y, so I just need to set one equation equal to the other equation. Since y equals 10x plus 4 in the first equation, and in the second equation y equals 7x plus 13, I can substitute in 10x plus 4 for y in the second equation. So in equation 2, I have y, which is actually 10x plus 4, is going to equal 7x plus 13. So solve for x, subtract 7x, and subtract 4. Those cancel, So 10 minus 7 is 3x. 13 minus 4 is 9. So x is going to equal 3. And you go, oh, in 3 hours they'll have the same amount of water. Well, let's double check here. It seems like a reasonable answer, but how much water are they going to have in the tank? So let's put that into equation number 1. So y equals 10 times 3 plus 4. So y is going to equal 34. So in 3 hours, both tanks will have 34 gallons. That is a problem, because if you notice, neither tank is bigger than 30 gallons, so they can't contain 34 gallons of water. All right. That would be bad, because you're going to have water running all over your house. So even though 334 is a solution to this system of equations, it's not a viable solution. Okay, this solution isn't viable since neither tank can hold 34 gallons. Okay, so the solution (334) is not viable since neither tank can hold 34 gallons of water. Now, if one tank was a 50-gallon tank, this still would not be a viable solution, because if the other tank can't hold 34 gallons, it doesn't matter. They'll never be equal. All right? They can never have the same amount of water in them. Now, if you recall, back in chapter 2 or so, we worked with motion problems. That's distance, rate, time problems. And we always solved them using one variable. Now, distance, rate, time problems can also be modeled using 2 variables. In fact, I find them simpler, a little bit easier to solve them when they are in 2 variables. This is especially helpful when you're dealing with currents or wind. If you know anything about the jet stream across the United States, we have a steady west to east wind that acts as a tailwind when planes travel from the west to the east. So if you're flying from Seattle to New York City, you're going to have a tailwind. That tailwind will make your plane's ground speed faster. So it's actually faster for you to fly from the west coast to the east coast, because you're always going to experience a tailwind in the form of the jet stream. Now, when you fly from the east coast to the west coast, that tailwind becomes a headwind, and that decreases your plane's speed. So it's always a little bit slower to fly from the east coast to the west coast. So from west to east, your airspeed plus your wind speed is going to equal your ground speed. And from east to west, your airspeed minus your wind speed is going to equal your ground speed. Okay? Or you just simply know whether or not you're having a headwind or a tailwind. So a plane takes about 6 hours to fly 2,400 miles from New York City to Seattle. So if it's from New York to Seattle, that's against a headwind. At the same time, your friend flies from Seattle to New York City. His plane travels with the same average airspeed, but his flight takes 5 hours. find the average airspeed of the airplanes, and find the average wind speed. Okay, so from New York City to Seattle, this would be a headwind, excuse me, just in case you didn't know that. From Seattle to New York City, that's a tailwind. Remember making these lovely distance, rate, times tables? We're going to do it again. Distance, rate, time. So, it doesn't tell us the distance, does it? Well, yes, it does. It says it takes 2,400 miles. So from New York City to Seattle is 2,400 miles. From Seattle to New York City, still 2,400 miles. That's the distance. I don't know how fast the plane is going, but I do know how long it took the plane to get anywhere. So from New York City to Seattle, it took 6 hours. And from Seattle back to New York City, it took 5 hours. So since I was asked to find the average airspeed and the wind speed, I'm going to let A equal the airspeed, and I'm going to let W equal the wind speed. So against a headwind, that means that wind speed is not helping me, it's hurting me. So that's going to be my airspeed minus my wind speed, because it's going to slow me down. With a tailwind, it's going to help me, so that means my airspeed is going to have the wind speed is going to help it, so it's going to be A plus W. All right. Hopefully you remember distance equals rate times time. So if we think of that in consideration to that, I'm going to have two equations. The first equation, my distance, 2,400, equals my rate, A minus W, times my time, which is 6. And in my second equation, I'm going to have distance, 2,400. It's going to equal my rate, A plus W, times 5. Right. Now, I could distribute the 6 and the 5, or I could simply know that 2,400 is divisible by 6, and 2,400 is also divisible by 5. So since I would be distributing the 6 and the 5, I can take both equations and divide them by each one of these numbers. So I could take this entire problem here, this equation, and divide it by 6. I could take this entire equation here, equation number 2, and divide it by 5. So I can get a new equation number 1. 2,400 divided by 6 is 400. So 400 is going to equal A minus W. And equation 2 here, if I took 2,400 and I divided it by 5, that gives me 480. So 480 is going to equal A plus W. Now I have two equations with two unknowns, and I could eliminate W very, very quickly here. All right, because if I just added these two equations right now, W would go bye-bye. So 400 plus 480 is 880. A plus A is 2A. And the W's cancel out. So if I divide by 2, A equals 440. So my average airspeed is 440. To find my average wind speed, excuse me, I need to substitute into either equation. I would think that it would be easier to substitute into either one of these two equations because the numbers are smaller. So I'm going to substitute back into equation 2 here because W is positive. That's the only reason why. So if I take equation 2 here and I have 480 equals 440 plus W. Subtract 440. W equals 40. Okay, so the airspeed, average airspeed, is 440 miles per hour. And the average wind speed is 40 miles per hour. And we have solved our equation. So there's a problem dealing with distance, rate, time. Let's look at two more because we're going to get into a lot of these problems, and these seem to be the ones that give people the most trouble. So I want to have lots and lots of examples here. So example number 5, two cars leave town at the same time in opposite directions. One travels 35 kilometers per hour and the other at 40 kilometers per hour. In how many hours will they be 200 kilometers apart? So I have two cars. I'm going to aptly name them car 1 and car 2 because that's simple for me. Distance, rate, time. Okay. I know that I know what rate they're traveling at, and I don't know what time. So I'm going to let t equal time. And I'm going to let d equal distance, even though you might say, but I know the distance. Now we need to find out what distance each car is traveling. And we know the total distance will be 200 kilometers. Okay. So if my first car travels at a certain distance, we don't know what it is. It travels at 35 kilometers per hour. And we do not know for how long it's going to travel, because that's what we're supposed to be finding is t. Car 2 is going to be 200 minus however far car 1 traveled, because remember, the cars are going in opposite directions. Okay, it's kind of like this. So if this car traveled 50 kilometers, this one would have to travel 150 kilometers. So however far car 1 traveled, car 2 is going to be 200 minus that. So this car 2 is going to be 200 minus d. It's traveling at 40 kilometers per hour. Well, we do not know how long it is traveling. We still have no idea how long it's traveling. Okay. So if I make my two equations here, remember distance equals rate times time. So first equation for car 1 would be distance equals rate times time. For the second equation for car 2, distance 200 minus d equals rate, which is 40 times time, which is t. So there's my two equations. The first equation is already solved for d, so I'm thinking that substitution would be really, really simple here. So I'm going to substitute in 35t every time I see a d in equation number 2. So I have 200 minus 35t equals 40t. So if I solve this, I'm going to add 35t to both sides. That's going to give me 200 equals 75t. To solve for t, I'm simply going to divide by 75. So divide both sides by 75. And t equals 275ths, which would reduce. Okay. If you had 200 over 75, I wouldn't leave it as an improper fraction in this particular case, just because that's not going to make sense to somebody. So if you divide 200 by 75, you get 2 2/3. So I would not leave this as 8/3. I would definitely leave it as 2 2/3. So in how many hours will they be 200 kilometers apart? They will be 200 kilometers apart in 2 2/3 hours. There we go. And the last example, example number 6, we're going to talk about kayakers. The speed of a kayaker is 5.75 miles per hour paddling with the river current and 3.25 miles per hour paddling against the river current. If you've ever paddled a boat or rowed a boat against a current, you'll understand that it's difficult to do it against the current, and it's much easier with the current at your back. It's kind of like running against the wind, running with the wind, biking against the wind or with the wind, or flying with the wind or against the wind. It acts the same manner. So, excuse me. So what I need to do here is set up my two equations. It's asking for the speed of the river current. So I need to know what my paddling speed is too, because all I know here is distance. Okay? I know a rate, 5.75 miles per hour and 3.25 miles per hour. Okay? But you're like, that's a rate, but not really. It's with the current and without the current. So I don't have a time, and I need to figure out the speed. And you're like, but I have the speed. No, we need the speed of the river current. We don't need the speed of the paddler. We already know the paddler's speed. So let's do this. Let's let P equal the paddle speed. And let's let C equal the speed of the current. Okay, and we're going to go with the current, and we're going to go against the current. So, distance, rate, time. I don't have a time, but I really can do a couple of interesting things with this problem. If I know I'm traveling at 5.75 miles per hour and 3.25 miles per hour, if I tell myself my time is 1, I will know how far I've paddled. Because if I'm paddling for 1 hour and I'm paddling with the current, I know I'm going to go 5.75 miles. And I know if I paddle for 1 hour against the current, I'm going to go 3.25 miles. So what I'm going to do is I'm going to say that my time is 1. So with the current, in 1 hour, I will travel 5.75 miles because I travel 5.75 miles per hour. So if I'm only traveling 1 hour, I'm only going to travel 5.75 miles. And that's with the current. Against the current, I'm only going to be able to go 3.25 miles. Okay, so with the current is helping me. That means I'm going to have my paddle speed plus the speed of the current. Do pay attention here. You have to be paddling faster than the current. If the current is swifter than you are paddling, you are never going to go anywhere. You're always going to go backwards. So it's really important that you understand airspeed has to come first, paddle speed has to come first. Your speed has to be greater than the wind or the current or whatever you're fighting against, or otherwise you're never going to go anywhere. So against the current, it's going to be my paddling speed minus the speed of the current. So again, distance equals rate times time. So my first equation, distance 5.75, is going to equal my rate, P plus C, times 1. And my second equation is going to be 3.25 is equal to the rate, which is P minus C, also times 1. So literally, I can just ignore the ones. And I can, because if I distribute the 1 in, I get P plus C and I get P minus C. So knowing that, I have these two equations. So if I add these two equations together, C's will cancel. These two C's will cancel right here. Okay. Right in this area right here, these C's will cancel because one's positive and one's negative. So 5.75 plus 3.25 is 9. The C's cancel. P plus P is 2P. Divide by 2. And P is going to be 9/2, which doesn't make much sense to anybody, so I'm going to say 4.5 or 4.5. Okay, so that's my paddling speed. That doesn't answer the question I was asked. I was asked, what's the speed of the river's current? So I have to find the speed of the current. So in equation number 1, I have 5.75 equals P, which is 4.5, plus C, which I don't know. So I subtract 4.5. Okay, and you're going to get 1.25. equals c. So the speed of the current is 1.25 miles per hour. So there we go. So this is how to solve real-world problems, setting up tables, and setting up systems of equations. So the closure question for this lesson would be, what is your favorite method for solving systems of equations and why? So make sure you tell me why you like that method better than all the other methods.